Hello, Professor. This is Jayant, and now I'm going to show my demonstration of time series analysis. So, for this, I picked air quality of data of India from Kaggle, and starting with the dependencies. Due to some conflicts, I uninstalled and then reinstalled some important packages, and then data loading and initial inspection. Here loaded the CSV file and inspected its structure. By doing this, we just get an idea of what is the data structure and what are we working on. And then automated EDA with pandas profiling, my data profiling. So to quickly analyze data distributions, correlations, and missing values, I generated an EDA report using my data profiling. So that it gives us in-depth overview of the data set, like correlations, variable distributions, missing values, correlation map matrix we can see here, and also the variable distribution of each variable like this. So you can see this, and then manual EDA. I just used filtered the data set for like Delhi, set the data as the index and plotted PM 2.5 levels over time. So this helps us visualize air quality trends and patterns, seasonal patterns unique to Delhi. So we can see that. And then coming to data cleaning and pre-processing. After the initial exploration, we clean the data by filtering relevant pollutants and applying forward fill to handle missing values. So, and next comes feature engineering of extracting temporal features. We extract temporal features such as the year, month, date of week, and year. These are useful for capturing seasonal patterns in air quality. Next, for enhancing our model, I created a lagged and rolling mean features for the PM 2.5. So why this is because we're enabling our model to learn from past data points and smooth out short-term fluctuations. So because of that, we did this, and then clustering with k-means. So I used k-means clustering to categorize pollutant levels. So it helps us to detect clusters of similar air quality levels over time. So we visualize the PM 2.5 with different colors to identify the clusters and patterns year, based on year, and we can see this. And then based on and next comes anomaly detection using isolation forest. We mark deviations in the pollutant levels as anomalies. So here in this plot, the point plotted in red with unusual spikes and drops of PM 2.5 concentration are anomalies here. So we can see that. And then comes splitting the training and testing data. For, so 80 in 80 to 20 ratio, 80% of data for training and 20 for testing. So, and the target variable is PM 2.5. We have defined that. And then forecasting model with AutoVIML. So we use this to automate the model building and feature selection for PM 2.5 prediction forecasting. So, so we passed on the data, training data, target variable and the testing data, and set the evaluation score metric like R square. So based on this, we generate accurate predictions for PM 2.5 levels, and the output is we can see. So removing highly correlated features, how Sulov method works. So bigger circle denotes higher mutual info score with the target, and the thicker line denotes higher correlation between the variables. And here feature selection is done by XGBoost, and then linear model training. And then we can see the model mean absolute error is 23.9. MAPE mean absolute percentage error is 22%, and the root mean square error is 38. So next we can see the ensembled model with an accuracy of 23.5, mean absolute error of 23.5, sorry, and MAPE with 28% and root mean square error of 35.6. And based on full training data, finalizing the model, training again. Now we can see the plots of actual versus predicted, and also the residual plot as well. And we can see the metrics of different models and ensembling models, the accuracy, I mean error scores, root mean square error, and mean absolute error. And same plots for ensemble model as well, actual predictions versus and also versus actual versus prediction, and also the residual plots. So this is my demonstration of time series analysis. Thank you.